All right, so let's see, you guys saw all these examples of relativity. Let's go solve some problems. So this page right here, okay, quick recap these formulas. Here's time dilation formula. There's, should point this out right here. Anything with the subscript not, you guys remember that twin paradox story yesterday? So two different times, T versus T naught. The T naught refers to rocket twins time. The solid T refers to Earth twins time. And they experience different passages of time, right, relative to each other. V represents the speed of the rocket. Say if they start on the same planet surface and the rocket speeds up to some speed. And then C is the speed of light, a universal constant. There are a handful of universal constants in the universe. Nobody knows why they are what they are. Nobody knows why the speed of light is what it is, but we've just measured it to be that number. Okay. Okay, so solve number one real fast. We got this twin paradox. Made in this yesterday with you guys, but let's do it again real fast here. Earth twin and rocket twin stand on the surface of Earth. Rocket twin takes off, flies off in a rocket at some speed and counts some amount of time has to take by. So how much, when he goes back and meets his twin back further back on Earth, how much time does the Earth twin say it's gone by? Right, so we're going to use this dilation formula. Earth twin time is equal to rocket twin time divided by the Lorentz factor. Okay, so I'll plug in my numbers, you guys plug in your numbers, and as long as, I'm eventually going to pick this paper up and grade it. So instead of doing any labs or quizzes this week, just follow along with me, solve the problems with your numbers, and then if you do them right, you get the credit. And so Earth twin time is, okay, well, rocket twin on my paper says 24 hours. So rocket twin's been flying around for 24 hours at a relativistic speed. And that relativistic speed is, on my paper says 2.1 times 10 to the 8 meters per second. Okay? It should be something like 10 to the 8, right? Because 10 to the 8, that would be getting close to 3.0 times 10 to the 8, which is the speed of light. Okay? Oh, don't forget to square these speeds, right? Squared, squared. Or if you like, you could do one divided by the other and square it after the fact. That would be okay too. But all this has got to be grouped underneath that radical, something like that. Okay. So let's just go on to, no, what you can do is a shortcut here, if you like. Since I gave you something times 10 to the 8 meters per second for the speed of the rocket, you could just bump the speed 10 to the 8 in the unit for the matter. Okay. So it could save you a little bit of calculator work. So I'm going to take 24 hours, divide by the square root. Open up some parentheses because I'm square rooting everything, so just be safe. Because once I close the parentheses, stop square rooting. 1 minus, and I've got 2.1 squared on 3 squared, because the 10 to the 8 I just bumped. This calculator will automatically close the parentheses. Some calculators do, some don't. I'm getting 33.6 hours. Okay. That is what Earth twin experiences has gone by, and in rocket twins 24 hours. Hey, isn't that consistent with that story yesterday of Earth twin and rocket twin? Which twin became really old during the flight? That was Earth twin. Yeah, Earth twin says a bunch of time has gone by, 33 some hours. The rocket twin's like, no, only 24 hours, hardly any time at all. Okay, actually the first 3 questions are all that story, twin paradox story. We've got a mass dilation and a length dilation coming up. Before I go into those, I wanted to solve one for you guys real fast, just remind you guys how that works. I want to do some graphs, and then we'll go back to solving those problems. So I want to look at graphs for each of these dilations. So there's time dilation that we just did. There's, split this into like three parts. Okay. We're gonna do, let me do a mass dilation right here. So Earth twins perceived, here, M naught represents rest mass. Maybe you could call that rocket twin's actual mass. Right? But if you get it in motion, then what would Earth twin perceive that to be, right? Or actually a really good example of mass dilation that I should have used on this paper was particle physicists over at Large Hadron Collider underneath the border of Switzerland and France. When they speed up particles near the speed of light to relativistic speeds, they appear to be gaining mass. So we're going to look at that graph. Let's also look at a length contraction graph. L equals L naught multiplied by the Lorentz factor. Whoops, one minus b squared on c squared. I'll introduce that radical. Okay. Now, in the length contraction, that's like the example of that train paradox that you guys just saw. So let's do graphs. Each is a function of speed. So let's do time as a function of speed. Let's do mass as a function of speed. And finally, length as a function of speed. I wonder what these graphs are going to look like. Length as a function of speed. Okay. There's some things I want you guys to see from these graphs. So as we put these together, what do each of these graphs look like? Well, the slow speed you could go relative to something else would, of course, be 0. Right? So two objects are just not moving relative to each other, kind of like me and you. Okay. So what is one person's time relative to another person's time if you're not moving? Well, another way of saying that is if I count off 5 seconds on my watch, okay, and you guys count off 5 seconds on your watch, would we both agree that that was like the same length of time? Well, we should. I mean, we're all in the same room, not moving relative to each other. Is that consistent with this equation? Let's plug in 0 for v and see what happens. 0 meters per second. So 0 squared divided by anything is 0. 1 minus 0 is 1. Square root of 1 is 1. And t naught divided by 1 is just itself. So t would equal t naught if you plug in 0 for v. So I can put a point on this graph right here and call this t naught. Okay, and what this is saying is that then rocket twin and earth twin do agree on how much time has passed as long as they're not moving relative to each other. What I just showed you guys is actually a really important principle in science called the correspondence principle, which says that suppose you come up with some wacky new theory about how something works. I mean, I'm sure that special relativity was the wacky new theory on the block back in 1905. Not only should your new theory be able to explain new fringe phenomenon that the old theory couldn't, like the GPS satellites, where you have to adjust their atomic clocks, but also it should be, the new theory should be consistent with the already good explanations of the old theory. So before Einstein, there was Newtonian physics, and Newtonian physics also says that sure, nobody's moving relative to each other, everybody agrees on how much time has passed. And so this agrees with that. What's the fastest speed you could go? Well, maybe on this graph, maybe I'll take it up to c, which is the speed of light. Now, what happens if you plug in c? Let's try this out. What we're about to do is a process called a limit. So if you guys ever take calculus, you do something very similar to what we're about to do here near the beginning of that class. If you do c squared over c squared, that's 1. Okay. Now, you can never quite get up to c, so maybe this would be like 0.99999, right? Almost 1. 1 minus 1 would be 0. Square root of 0 is 0. T naught divided by 0. Hey, what is anything divided by 0? And it's not 0. Undefined infinity, right? And on the graph, wouldn't that show up as a vertical asymptote, right? Something like that. Okay. That's why you can never quite reach it, right? You can never quite. So this graph is going to look kind of like this. Right? It would just go up forever. Right? So that if you were to reach the speed of light, say time would go infinite. What would that look like if you were a rocket twin? Say flying around the universe, and you were going like 99.99999% the speed of light. To you, what you would see is, well, it's like a super old Earth twin, right? The entire age of the universe would just like flash before your eyes, right? And if you were to reach the speed of light, now nothing with mass can reach the speed of light, but if you were, then the universe would just be over in an instant. Like the entire existence of the universe would just flash by in a second. I've heard the case made that if you were, say, a photon of light, like traveling at the speed of light, anything that does not have mass necessarily does travel at the speed of light through space. That time does not exist from your point of view. Right? This is one of the questions that Einstein was asking himself when he came up with this whole theory in the first place. So what would it be like to ride along with a ray of light, say, along with a photon? Well, time would actually not exist. There would just be a giant flash and the whole universe would be done. Interesting thought. How about mass dilation? Well, these two formulas have the exact same structure, don't they? So you think this graph's going to look pretty much the same? Okay, m naught, and then put c right here, vertical asymptote. Very similar looking graph. Same reasoning. Okay. So again, if everybody's at rest relative to each other, plug in 0 for 0 meters per second for V, then everybody can agree on what some mass is: mass of a person, mass of a particle, right? And then, but if that mass heads towards the speed of light, then it becomes infinitely massive, as seen by an outside observer. That'd be interesting too. Probably take a bunch of energy to get it to speed up to that speed. It'd be crazy. And finally, length dilation. Okay. Now this, this one's multiplied by the Lorentz factor instead of dividing by. So I wonder how that's going to be different on this graph. So plug in our boundary conditions. So if you plug in 0 for V, so everybody's at rest relative to each other. Say 0 divided by c squared is 0. 1 minus 0 is 1. And L naught multiplied by 1, because square root of 1 is still 1. Well, that'll just be L naught. Okay, well, this is good too. This also agrees with the correspondence principle. So if everybody's at rest relative to each other, everybody can agree on the lengths of things, the size of things. Right? Now, what if you take this all the way to c the speed of light? See what happens if you plug this in as a limit. C squared over c squared is 1. 1 minus 1 is 0. Square root of 0 is 0. L naught times 0 would be 0. It'd be like this point on the graph. If you remember how to graph square root functions from, say, a math class, maybe pre-calc or trig, possibly. Wouldn't that square root curve look kind of like this? Like a nice square root curve? That is what that would look like, wouldn't it? What would that mean if you were a rocket twin and you approach the speed of light in terms of like length contractions? Now remember back to that train paradox. So as the train moves at a relativistic speed, everybody thinks the train gets shorter, but on board the train, you also think the world around you also gets contracted. Right? So we've got different frames of reference. Right. So everybody would see your rocket ship get infinitely short until it gets, or sorry, I should say like 0, right? Like 0 length. But from your point of view, traveling along in the rocket, you would see the entire universe also contract down to 0 size. So maybe if you're a photon of light traveling at, of course, the speed of light, not only does time not exist to you because the entire universe is over in a flash, but maybe space doesn't really exist from your point of view either. It's kind of like you'd be bouncing around, you'd be like everywhere and every when. If you were a photon, right, from your point of view, space and time don't really exist. Interesting. Interesting consequence of all this stuff. All right. So that's a fun little side thought there with those graphs. Let's go back to these problems. And so number 2 is a mass dilation. Remember the first 2 questions are twin paradox type questions. So number 2, got a mass dilation. Earth twin stays on Earth, rocket twin flies around a rocket. I gave you some relativistic speed and the speed of light. Right. Now, what would the rest mass be so that you get this particular dilated type mass? Right? I really do need to go back and change the story and make it about a particle over at Large Hadron Collider, because this is something they actually do see all the time. Maybe you could say we're looking at like 100 nanograms of particles. What was the rest mass of these particles? And just change the story a little bit. The math is going to be the same. So we're going dilated mass is equal to rest mass divided by Lorentz factor. You're solving for the rest mass in this case. So there's going to be one algebra step, and that's to take this Lorentz factor and cross multiply it up. So wouldn't the rest mass be equal to the dilated mass multiplied by the square root? Wouldn't that be true? Okay. And then just plug stuff in. So looking at the dilated mass, now my paper says 100 kilograms. So what was rocket twins' rest mass when they go back and meet and steps on the scale and all this? Well, his dilated mass appears to be like way more massive than he actually is. This Lorentz factor, by the way, is bounded between 0 and 1. If you plug in those boundary conditions for V, V could be 0 up to C. So this whole square root is going to be somewhere between 0 and 1. It's going to be a decimal. Okay? So 1 minus, I have 2.3 times 10 to the 8 meters per second. Don't forget to square that compared to 3 times 10 to the 8 meters per second, and square that one too. This whole thing's being square rooted. So what is 100 multiplied by the square root of, open some parentheses, 1 minus, open some more parentheses, just to be super safe. I'll go ahead and cut through the 10 to the 8 part because 10 to the 8, 10 to the 8, cancel out. We're going 2.3 squared over 3 squared. And the number I'm getting is 64.2, that's kilograms. Okay. So that is Rocket Twin's actual rest mass, according to the numbers on my paper. Okay. So he was back on Earth, stepped on a scale, so 64 kilograms. Then he jumps up in a rocket, and if Earth Twin is somehow able to ascertain his mass, then he would appear to have to be 100 kilograms. Okay, so kind of silly example, but that's a application of that dilation question. Now, number 3, I actually do like this scenario a lot. I think the story fits. So we're looking at a length contraction here, a lot like that train paradox that you guys saw just a few minutes back. So Earth Twin stays on Earth, Rocket Twin flies off in a rocket at some relativistic speed, which I did not give you. But I did give you the rest length of the rocket. The rocket was so many meters long. And then what's going on is that Earth Twin is looking through a telescope and saying, whoa, bro, what happened to your rocket? It's super short. And if you know exactly those two lengths, the rest length and the dilated length, you can calculate how fast that rocket has to be going for that to be true. Okay? Now, keep in mind, if you're along for the ride with Rocket Twin, you don't notice anything weird about the ship. Time still beats 1 second per second. You break out a tape measure and say, no, the length of my ship is still 8 meters long. But Earth Twin say, no, it looks like it's only 5 meters long through my telescope. So what is the speed of this thing? So we're going to go L is equal to L naught multiplied by the Lorentz factor, 1 minus v squared on c squared. Square root of that. Okay. And we're solving for v. Now, I did set this up in a way that you have to go on an algebra quest. So 2 ways you can go about this. One is that you can plug in all the numbers first and then do the algebra process after the fact, and that's perfectly fine. Remember, the last step should say v equals something. Alternatively, and what I'm going to do with you guys, what I normally do with my AP kids, but I'll do it with you guys here, is to solve this in terms of variables, so you get a general expression solution. And you'll still get v equals something, but it'll be in terms of these variables, and then you can plug in the numbers after the fact. Let's do that. Let's go through this algebra process in terms of variables. So I'm going to do process get v equals something. First thing I'm going to do is divide down L naught. Divide both sides by the rest length. So L on L naught is equal to the square root. Okay. Next thing, well, maybe I should square both sides. We do that in this blue ink right here. If I square both sides, right, would that undo the square root? I should have picked a different color, but anyway. All right, so that would be like L squared on L naught squared is equal to 1 minus b squared on c squared. Okay. Okay. At this point, I see 3 terms. If you know what you're doing, by the way, just go ahead and stay ahead of me and get to the answer. But if you need an algebra review, I see 3 terms. I'm going to do a double swap here. I'm going to take this term right here, b squared on c squared, and add that over to the left side. At the same time, I'm going to take this L squared on L naught squared and subtract that over to the right. Okay? So that'll look like this. V squared on C squared is equal to 1 minus L squared on L naught squared. Okay? A little double swap there. Okay. 2 steps away, I'm going to cross multiply with the C squared. So V squared is equal to c squared multiplied by 1 minus L squared on L naught squared. And finally, take the square root of both sides. Now I got v equals something. Square root of c squared is just c, multiplied by square root 1 minus L squared on L naught squared. Interesting, like that kind of looks like a sort of Lorentz factor itself, doesn't it? That L squared thing. Definitely looks relativistic. Right, so now let's plug in some numbers. So how fast v, does the ship have to be moving? Well, I know what speed of light is. It's 3 times 10 to the 8 meters per second. I'm going to multiply that by a big old square root. 1 minus, okay, now here's where there's disagreement about the length of the ship. Right, so the rest length is in the denominator. So that's Rocket Twin's perspective. It says 8 meters long. And Earth Twin looking through a telescope says, no, it looks like it's 5 meters long. Don't forget to square those values, square. Okay, like that. Okay. And now all else to do is to correctly plug that into the calculator. Way I'm going to do this is I'm going to leave off the 10 to the 8 part in the calculator and just multiply that back in after the calculation. So I'll do 3, skip this up a piece, multiplied by the square root, maybe with some parentheses just to be safe, 1 minus, open parenthesis, 5 squared on 8 squared. So the number it's telling me, V, is equal to, I'm looking at 2.34. Now, if I go back and put in the 10 to the 8 bit, that's times 10 to the 8 meters per second. Just got the unit all there. Okay. So that is how fast that ship had to have been flying. Okay. Which, what is that compared to the speed of light? That is 78% the speed of light. Ooh, that would have been a good question too. Maybe I should ask that. So if you're going 78% the speed of light, then your rocket would appear shortened from an Earth frame reference from 8 down to 5 meters. Okay. You guys got yours too? Good. I mean, this step right here is a general solution for everybody, although it's good to be able to do the algebra to get to that point and just plug stuff in. 1 point. Yes, good. Right, let's put a pause on number 4, and I'm gonna hit these two down at the bottom of the page, number 5, number 12, and we'll come back to 4. So number 5, where does time tick faster due to special relativity? The surface of Earth or inside a spaceship moving near the speed of light. So for Earth twin or for rocket twin? Hey, which twin got really old, Earth twin or rocket twin? Earth twin. So that would have to be the answer, right? Okay. So remember, if you're in either frame of reference, time beats 1 second per second for you. But if these two guys break out telescopes and they're looking at each other, here's what Earth twin sees looking through the window of rocket twin's ship, and maybe sees a clock hanging on the wall. So rocket twin's clock looks like it's doing like tick, tick, tick. And then rocket twin looking back at Earth twin sees Earth twin's say like this clock right here. So you can see it from space. You go like something, right? Okay. How about scoot over to number 12? Where does time tick faster due to general relativity? Now remember, general relativity, we're incorporating mass. You guys remember on a GPS video, you saw that mass causes time to slow down also. So let's see, the further away you are from a mass, probably time would speed up, and the closer you are to mass, time would slow down. Okay. Did you guys happen to watch a movie a few years back called Interstellar? Interstellar? Okay. Okay, so there's some scenes in that movie where they, this comes into play. I forget where they were visiting. It could have been, it was next to some large mass. It could have been like a black hole or some very, very large mass. And the people who were on the ship went and approached it and came back out. And to them, it was like a few minutes, like 10 or 20 minutes. Right? But whoever was waiting for them back in, the rest of the universe was like many years have gone by, and I've been waiting this whole time. So that would be, if you compare these two, surface of Earth, surface of the moon, where does time tick faster? Maybe another question you could ask is, who has less gravity? Less gravity. And the answer to that is surface of the moon. Yeah. Now, keep in mind, this is a very tiny, tiny, tiny subtle effect. So how about those Apollo astronauts back in the 1970s bouncing around on the moon? Did time be a little bit different there than back on Earth? Yeah, but you would really need an atomic clock to even measure the difference. So to get a significant difference, well, you guys saw our GPS satellites. It's enough of a difference that you have to consider that for GPS to work correctly. Okay, let's go back to number 4. Number 4. So this is a mass energy equivalence question. Some given amount of mass is converted completely into energy by a nuclear reaction. Okay, nuclear reaction. The energy associated with that is E equals mc squared. How many joules of energy have been produced? And so I gave you some mass and some number of kilograms, gave you speed of light. Okay, so just run equals mc squared. Now I should tell you guys that I'm assuming here that all the mass has been converted completely into energy. So this might be maybe a matter antimatter reaction, something like that. Now, antimatter is like the opposite of matter. Like everything in this room is just made of matter, right? Physicists over at CERN, over in Switzerland, have created antimatter. And if antimatter ever comes into contact with matter, then it immediately annihilates and releases a bunch of energy. It's like a pure energy, pure equals mc squared. So to store it, you have to like keep it in like a vacuum chamber and keep it magnetized, levitating, where it does not touch anything. Like even the air is made out of matter. Right? One of the mysteries of the universe is why, starting back from the Big Bang, why there is more matter than antimatter at all. That's one of the mysteries of science is like why they weren't created in equal amounts and just immediately annihilated each other. Why does it appear that there's more matter than antimatter in our universe at all? Okay, so let's run the equation because the equation is pretty straightforward. E equals mc squared, mass energy equivalence. So on my paper, I have 6 kilograms of mass. Let's say this is all antimatter and going to convert it completely into energy. How much energy am I getting? Say 3 times 10 to the 8 meters per second is the speed of light. Don't forget to square that. Now, speed of light squared. I mean, you guys remember how exponents work? 10 to the 8 squared, isn't that like 10 to the 16? That's a 1 followed by 16 zeros. Woo! And then 3 squared is 9. That's almost another 10. Wouldn't this be like 10 to the 17? Okay. Now that's a crazy, crazy big number. That's a number that's just unfathomably big. Right? 6 kilograms. That's probably like a pretty good sized bowling ball. Right? So 6 times 3 times 10 to the 8 squared. I'm looking at, yeah, it looks right. It's a number so big it doesn't even fit on my calculator screen. It's 5.4 times 10 to the 17 joules. The calculator just told me scientific notation because or there's not enough places on screen. Okay. Let's go that. And actually, that is such an abstract idea because that's a crazy big number. I did want to put that in context for you guys. So that's what the question number 6 is about. Question number 6 is also E equals mc squared, but has a story tag to it. It goes like this. You are a resident of a spaceship moving between stars in the galaxy, and you want to sustain some decent standard of living. So you're going to consume energy at 40 kilowatt hours per day, which is a pretty Western standard. So how much energy do we use in the States as part of a developed country? Well, think about what kind of energy you use every day. It's not just the energy in this room. There's lights and projection and air conditioning, and you got to plug your phones in. Yeah, and it's not just the gasoline you put in your tank to drive your car around, although those are enormous amounts of energy, but everything you buy, there was a whole assembly process behind that, all the food you eat, there was some like agriculture process. If you add up all that energy that's used, this is a pretty Western standard right here. So we're up in space now, we want to maintain that standard of living, so we're using energy at this rate. And here's what we did. The ship's fuel storage contains a given amount of nuclear fuel per resident. And let's say this is antimatter, so pure, all of this is going to go to energy eventually. How much mass per person do we have? 0.01 kilograms. Ooh, guys, how many grams is that? 0.01 kilograms. Roll the decimal 3 places. It's like 10 grams. 10 grams. Oh, I got 10 grams right here. Here's 10 grams. It's your smallest lab weight. It's like a pea coin. You could put this in your pocket, you wouldn't even know that it was there. Right? So what if this was pure antimatter and you went through some matter antimatter reaction and so that you could use energy at a rate of like Western developed country. Okay? And the question is, how long would it last you? So we're gonna have to save this one for tomorrow, but you can tell just by looking at the answer choices, we're talking about order of magnitude of tens of thousands of years. Whoa, so put this all together. This amount of mass converted completely into energy, using energy at the rate that you use in your normal everyday lives. This would last you 10, or at least 10,000 years. Yeah. So think on that, think about that, but that's gonna be our pause point today.